Morning, everybody. Again, this is another section of Bed Talks. I hope you're doing well. I'm going to be talking today about chapters 14.6, the section 14.6, which covers the ideas of directional derivatives, gradients, and again, tangent planes in the end as well, too. And with this idea, we're going to hopefully, encapsulate a lot of interesting ideas in this entire section. And this kind of wraps up chapter 14 in a really interesting bow that will kind of spearhead going forward. So I guess the first thing we want to remind ourselves is what the ideas of partial derivatives are just in general again. So I kind of had discussed in this previous chapter, section, that the idea of partial derivatives comes down basically to if I am at a point on a surface and I move in the positive x direction, how fast is my height changing? And again, that would be the derivative with respect to x, right? This is partial with respect to x. If I then ask the question, if I move in the positive direction with respect to y, in this direction here, how fast is the height changing at that point? And this is just in the x direction and the y direction. And I mean, there are many other directions we can go in, right? So what if I ask the question, for instance, if I go in this direction, how fast is the height changing at that rate? And that's a really important question. And so how do we start to maybe think about that in general? How do we calculate that? So a couple things that we want to know about is this idea of a directional derivative. And it comes from the ideas of weighting, kind of the direction you go in and weighting the fx and fy components in some way. So I'm going to let this be a unit vector here, AB. I'm reducing 2 dimensions at first. So let's imagine now that I'm going in this direction here. And this is A and this is B here. So again, what I'm trying to say is I'm going kind of, if you can see, if I want to take in some way in the A direction, in the direction of the x-axis here, I'm going A amount, and then in the direction of the y-axis, I'm going a B amount. And so you can kind of think about that. I would like to have, say, like, okay, A times the derivative with respect to x plus B times the derivative with respect to y, because that's kind of what I'm doing. I'm going in the x direction, A amount. I'm going in the y direction, B amount. And that's kind of what this kind of goes out to be. So it's very important that this is a unit vector. Note that this must be a unit vector here. If it is not a unit vector, you must make it a unit vector. It's important. So what we then say is the directional derivative of f in the direction of u, which basically is again asking the question, how fast, what is the rate of change of my function height as I move in the direction of u? This is a very, very, very immediate and very localized value. It changes immediately as I keep moving. So you have to be pretty careful. But if I want to find du of f, which is kind of the directional derivative of f in the direction of u, I'm going in this direction of u here. How do I find this? Well, what we do is we do a times fx, the number a times fx, plus b times fy. So we kind of just weight that. So we find fx and we find fy. We find the derivatives with respect to x and y. We multiply them by a, and we multiply it by b, and add them together. That's kind of how we do it. Now, there's another way we can kind of write this. If you note here, we can write this as kind of a dot product. Because if you see, I can kind of rewrite this here. AB is its own vector, right? And we also have here, we have fx and fy as its own vector too. And what's cool here is I know what this vector is, this vector u, right? This is my unit vector, and the dot product of fx and fy. And this again is actually probably a better way of interpreting what the directional derivative is. I have u, I'm going in direction u, I'm taking the dot product with fx, fy. Now what is this guy, right? What is that value? That value, fx, fy, is actually a really important value. We call this the gradient. So let me just kind of reference something here very quickly. So as a reminder, what is the gradient? So we say here that duf, let's say f is just a function of x and y here. But this extends very, very quickly to multiple dimensions, higher and higher and higher. The directional derivative can be then rewritten as the gradient of f dot product with the unit vector, where the gradient of f is equal to fx, fy. The gradient of f here, we'll talk about some of the interpretations of this going forward. But the gradient, this is called the gradient. We have this upside down triangle. It is a vector that is of the derivatives with respect to each one of the variables in my function f. So if I had a function, I have a function of r, s, and t, for instance, the gradient then of f would be f sub r, f sub s, f sub t. We would just take derivatives with respect to each one of the variables and put them in a vector. So as a reminder, a gradient is a vector here. Okay, the directional derivative, though, because it is a dot product, this is going to be a number. It's going to be a scalar value, which is important, right? I should be telling you, as I go in some direction, how fast is my height changing is a number, right? Not that. So this gradient here, this gradient of f, is going to play an important role. So as a reminder, we can try to do a problem really quickly about what this really is. So let me just do it to make up a problem. If I have this function f of x, y, and I have something like the natural log of x plus y here, something like this, right? I have something like that, and maybe, yeah, I think that's pretty good for right now. So I have the natural log of x plus y, and I'm taking the point here, maybe, 0, 1. Okay, the point 0, 1, and my goal here is to find the directional derivative in the direction of a vector v, which is going to be the 3, 4. Why don't we say? I want to find the directional derivative in the direction of v. How fast is my height changing in that direction, going in that direction? Now, a couple things we need. Okay, we need a couple things. One, I need to find my u. Now, I'm given a vector 3, 4, but I hope you can see here, this vector is not going to be a unit vector. It's not going to be a unit vector at all, because the magnitude of v is 3 squared plus 4 squared, which is square root of 25, which is going to be 5. So we note here that my magnitude of v is equal to 5. This has to be 1, right? My direction has to be 1. So what I do is to create a unit vector going in the same direction, I'm going to divide this vector v by 5. Right? My unit vector will then be 3/5, 4/5. This is going in the same direction now, but I'm actually going in the same direction, but now it's a unit vector, and I can utilize this formula. It has to be. That's the first thing you should always check. Is my direction a unit vector? If not, you got to make a unit vector by finding the magnitude and then dividing by it. Now, what I next have to do is I have to find the gradient. The gradient here can be calculated pretty quickly. Right, the gradient of f is going to be the derivative of this guy with respect to x, which is just 1 over x plus y. And similarly, the gradient of f with respect to y is also the same thing, 1 over x plus y. Now, for these problems, if you're finding the directional derivative at a specific point, plug in the point first to this formula and go from there. So what we see is I find the gradient at the point 0, 1 here, at the point 0, 1, is going to be equal to 1 over 1 and 1 over 1, which is just going to be the direction 1, 1. That means the gradient of f at the point 0, 1 is equal to 1, 1. Okay? And so therefore, the directional derivative of f at 1, 1 is just equal to the dot product of the gradient of f and u. So just 1, 1 and 3/5, 4/5. 1, 1 and 3/5, 4/5, which just comes out to be basically 3/5 plus 4/5, if I do that out, which is just 7/5. So this says, if I go in the direction of 3, 4, I go, if I'm on a point, if I'm on the surface here at the point 0, 1, if I plug in 0, 1, this is going to be 0, 2, right? So I'm on the point 0, 1, 0 on my surface. I then look in the direction of 3, 4. If I start to move in that direction, the rate of change is going to be approximately 7/5. It's going to be approximately, I'm going to be going up in my direct, I'm going to be going upwards in 7/5. My height's going to be increasing at that rate. So I'm kind of going in, something like this direction here. That's kind of the goal. So this is how you calculate the directional derivative. Now, one question you might ask yourself, and actually a pretty cool question, would be, okay, well, what is, if I was standing at the top of a mountain, right? Or if I was standing at the bottom of a mountain, and I wanted to get to the top of the mountain the quickest. right? My goal would then try to be to find the direction of maximal rate of change at every single point, right? Because I want to just get to the top. I don't care about my health at all. I want to get up to the top of the mountain as fast as possible. I'll even rock scramble or whatever I want to do. I'm at the bottom of it, and I want to get to the top as fast. So I want to find the directions that have the highest rate of change as quick as possible. Can I find that? So let's try to think about that really quickly. So I'm going to leave this up. Here's the formula for the directional derivative. My goal now, and this is where we're going to start to become like some form of an interpretation of the directional derivative and what the gradient actually is. Let's say I want to maximize this, right? Well, this is really tough to think about as I want to maximize, right? I want to find the direction. I want to find the direction u such that this is maximized, right? I want to find the direction u such that this formula is maximized, my fastest rate of change. So in order to do this, I have a dot product here. Now, I have another interpretation of the dot product, right? I know that if I have a dot b, what I could do is I could find the magnitude of a times the magnitude of b times cosine of the angle between them. This is a nice way to kind of write that. So let's write the same exact thing here. U cosine of theta. And as a reminder, theta here is going to be the angle between u and the gradient of v. Okay? Now, what do I know here? I know that the unit vector, this u is a unit vector, so I know the magnitude of this has to be 1. Okay? Because this goes away because this is equal to 1. So now, my goal is to figure out how to maximize this value. How do I maximize this? Well, I have no control over the gradient of f. That's just a number. That's just there. I have control over this cosine of theta, though. Again, this theta is the angle between, this theta here is the angle between the gradient of f and u. Right, this is that theta here. Now, how do I maximize this? What is the maximum that cosine can be? Maximum that cosine can be is 1. Right? This gets maximized when cosine is 1. And when is cosine 1? Well, that's when, I hope you'd agree, that theta is equal to 0. Right? So when theta is equal to 0, this is equal to 1. And so therefore, at theta equal to 0, this is maximized, right? Cosine can never be bigger than 1. And so therefore, this is equal to the magnitude of the gradient of f. What does a theta equals 0 mean? Well, theta equals 0 means that u and the gradient of v are going in the same direction. They are parallel. So what does this all imply in total? This implies that the gradient of f actually gives me the direction of maximal increase. It gives me the direction where if I go in that direction in the xy plane, if I go in that direction in the xy plane, I'm going to be increasing my function to the highest value, right? I'm going to be increasing at the highest rate possible. And so what is that value? What is that rate of change? That rate of change is actually the magnitude of the gradient of f. That's all it is. So in total here, this means, again, let me just reiterate, the gradient of f in a two-dimensional sense. I want to be very careful here. Think about this. It comes up in a couple different ways. In a two-dimensional and even a three-dimensional sense in a certain way, but we can talk about that later. In a two-dimensional sense, this really means if I go in a direction and it is in the direction of the gradient, I'm going to be moving upwards. I'm going to be moving upwards in my fastest rate possible. I'm going to be increasing at my fastest rate. And that rate is the magnitude of the gradient of f. So going back to my original problem that I had, if I wanted to solve then, if I was having my function here, my f of xy, which was equal to the natural log of x plus y, at the point, 0, 1, at this point 0, 1, and I wanted to find, if I'm at the point 0, 1, what is the direction I need to go in to increase my function the fastest? Right? What is the maximal rate of increase as well? What is the direction and the maximal rate of increase? I found that the gradient of f at 1, 1 was equal to, at 0, 1 was equal to 1, 1. And so therefore, this direction, if I go at a 45-degree angle in that direction, that is a 45-degree angle, that is going to be the direction of the maximum rate of increase. If I go in that direction, I'm going to be increasing at the fastest rate possible. And what is that rate? Just the magnitude. which I hope you'd see, is just the square root of 2. So this means that if I am standing at the point 0, 1, 0, right? If I plug in 0 and 1 here, I'm going to get the point 0, 1, 0. I'm standing at the point 0, 1, 0. My goal is now to figure out which direction to go in. And I want to face somewhere in the xy plane that tells me which direction to go in. I'm going to now face in the direction of 1, 1. Here's the direction of 1, 1. And I go in that direction, I'm going to be increasing at the fastest rate possible. And that rate will be at the square root of 2. That's what this means. So if you ever need to figure out maximum rate of change or direction of maximum rate of change, that's where this comes into play. So now, if I want to extend this a little bit more, this extends to any dimension, right? This idea here. So if I had a function of f where I have 3 or 4 variables, this goes very, very quickly too. You'll always need u to be of a magnitude of 1. Always make sure of that. Now, going forward, we can then start to think about the idea of tangent planes. And we had brought this idea up back in another section as well, where I had, I was trying to find the equation for a tangent plane of something like f of x, y, right? Something like this. Now, but what if I wanted to find, what if I have a function like that is kind of implicit? Let's say it's something like this, where I have some function like xy plus xz plus yz is equal to 3. Yeah, something like this. And I had the point, 0, 1, 3, for instance. And I wanted to find the tangent plane to that point. Now, what we could do a couple of different things here, honestly. We could, if we wanted to, we could maybe solve for z here, but that seems a little bit tedious and maybe unnecessary, because that would then require us to have actually use the, probably the quotient rule to solve for my partial derivatives of x and y. But what this actually comes out to be, and one thing we should kind of think about here going forward, is what are the other ways that I need to write the equation for a plane? I need the equation for a tangent plane here. Now, what we can say then is, again, I need 2 things when I want to write this. I need a times x minus x0 plus b times y minus y0 plus c times z minus z0 is equal to 0. This gives me the equation of a plane. And here is my normal vector, and I have a point x0, y0, z0. Now, I have this surface. This is actually a level surface. I can rewrite this if you see. This is some function of x, y, and z. Some function g. We can call it. Now, if I call this function g, what I can note here is if I just left this 3 off, if I just said, g of x, y, z is equal to this entire function here, this is going to be a 4-dimensional object. I hope you'd agree. I have an x, y, and a z, and I give you a 4th dimension. So it really doesn't make sense for me to think about a tangent plane with 4 dimensions, right? Don't think about anything really 4 dimensions. It starts to get really, really tough. But so what we do is we say, okay, well, what if I tell you that g of x, y, z is equal to 3? And this is the same exact way as I kind of think about in terms of level curves, right? If I have some function f of x, y, maybe x squared plus y squared, and I say this is equal to k, right? What is this doing? What I'm doing is I'm lopping off, I'm taking my function here, a 3-dimensional object, and I'm taking it z, right? I'm slicing it at z and seeing what that contour is going to be, right? Seeing what that contour of the intersection between z equal to k, my height, and the surface itself. Here, though, I am taking a 3-dimensional object and slicing it, right? I have a 4-dimensional object and I'm slicing. I'm telling you, I want to find out all the x, y, and z's such that this function g of x, y, z is equal to 3. This is called a level surface. Okay, this is called a level surface. Now, what a level surface is again where a function of 3 variables is equal to a number. Now, equal to a certain function value. It's just a different thing because we don't have curves now. We have actually a surface. This is actually a surface here, some closed object. So what we want to think about now, it doesn't have to be a closed object. I apologize. It just has to be some object in 3 dimensions, some surface. So now what we want to do is we want to find out what this normal vector has to be. And you can find, which is pretty cool, that this normal vector here, it can be actually calculated by the gradient of g at that point. So what you would do is the normal vector here, it's just calculated by the gradient of g at the point x0, y0, z0. And if I calculate this, This is also another interpretation of the gradient. Now, I want you to be very clear about the difference between the interpretations of a two-dimensional gradient and a three-dimensional gradient. A two-dimensional gradient, as we had seen, gives me the direction of maximal increase. If I do a three-dimensional gradient, this now gives me a normal vector to the tangent plane. Because now I'm thinking about things instead of level curves, I'm thinking about things in terms of level surfaces. And this is actually a really important distinction here. They both have their own place and they both have their own importance here. We can also get a normal vector if I just had something of f of x, y by moving something over and making something three-dimensional like this. We can get a normal vector. I'll show you that in 2 seconds too after we do this problem. But again, the idea here is if I have something of 3 variables, you want to get them all on one side. If they're not all on one side, please do. If it was something like this, 3 is equal to, x, yz, negative yz. What you would want to do is you want to get all of the, all of the variables on the same side. You get all the variables on the same side by moving this over. You would take this function, you name this as g of x, y, you take the gradient at the point x0, y0, z0. And that would be used for your a, b, c. So let's kind of go ahead and do this, just so you kind of see what we do. We're going to take this gradient now. I take this gradient of g, and with respect to x, this just becomes y plus z. This goes away because there's no respect to x. If I take this gradient with respect to y, we will then get x plus z. And lastly, if I take this with respect to z, I would get x plus y. I then calculate the gradient at the point 0, 1, 3. If you'd note here, if I plug in 0, 1, 3, 0, these 2 terms would go away, and I'm left with 1 times 3. And so this satisfies that. That's why I know that I'm on this point. The gradient of 0, 1, 3 would then be y plus z, which is 1 plus 3, which is 4, x plus z, which is 0 plus 3, which is just 3, and x plus y, which is 0 plus 1, which is just 1. Now, what does this tell me? There's 2 things that this really tells me. Firstly, it tells me that this is the normal vector to my plane, to my surface, at the point 0, 1, 3. Okay. Now, this also tells me, I know for a fact, this also tells me it's the direction of maximal increase. So, what is this really saying? Imagine if I made this a 4 now, or this g of x, y, z, this function g of x, y, z here. I now take the gradient of this. This is now saying that if I go in this direction at this point, I am going towards the direction where g of x, y, z is increasing. So maybe the next level surface, maybe when this is 4, this gives me the direction I need to go in to get to that other surface where this is equal to 4, and so on and so on. So it's kind of telling me, if you want to think about it, it's kind of like Russian nesting dolls in some way. I have this I have these concentric, you can even think of spheres. I have concentric spheres. If I find the normal vector to a sphere, right, that has different radii, it's telling me the direction to get to the next sphere that's bigger than it. And so on and so on. It goes from like that. So it's kind of like the Russian nesting doll thing. So, but this also then tells me that this is a normal vector, and it should be. And we'll talk about that one last thing in 2 seconds here. But here what we're going to do is this is 4, 3, 1. And so therefore, if I want to find the tangent plane, what I do is this becomes 4 times x minus 0 plus 3 y minus 1 plus 1 z minus 3 is equal to 0. And this is my tangent plane. This is the scalar equation. If you notice here, this would become 4x plus 3y plus z. And then you would get a negative 3 and a negative 3. So this would be 6. And so this is the tangent plane approximation to the surface. And this also tells you now, again, this tells you the direction that's going. And it also, if I find the magnitude of this will tell you the magnitude of the direction, the magnitude, how fast is my rate of change changing? How fast is this actually changing from a 3 to a 4 or 4 to a 5 or something like that? So this is the idea. Now, lastly here, we want to think about, and this is the last thing I want to at least discuss here, this idea of level surfaces and gradients. Well, you kind of had mentioned one thing that I kind of said, right? Is what is the the interpretation of the gradient with a level curve, or the gradient with a level surface? Here, you might say to yourself, "Oh, the gradient to level surface should be orthogonal to each other." I think it should be. Let's think about why. So if I do this, again, I write that my directional derivative here, du of f, is equal to the gradient of f dot u. My goal now is to figure out the direction, basically, that this vanishes. What do I mean by that? Well, where is this 0? When is that 0, right? When is this 0? Well, if I just write it like this, I hope you can see something pretty nicely. If I tell you that where does the directional derivative vanish? Again, what does that mean? This means that which direction do I have to go in where my function value does not change? My height is not changing. I am staying the course. I'm not going down, I'm not going up. Which direction do I have to take such that it is equal to 0? And by this definition right here, I hope you'd see that this implies that the gradient of f must be perpendicular to u. It must be orthogonal because the dot product is equal to 0. So what does that mean? Let us say I have a level curve. Okay. This level curve right here, this, I'll name this like k is equal to, some number. Right, z is equal to k. Imagine I take a slice at a level curve. Okay, there's a level curve. This entire level curve right here. I am not changing my height. If I stay on that entire level curve, I do not change my height one bit. I don't change it at all. So what I do is if I want to find the gradient, what I do is the gradient has to be orthogonal to the direction I would need to go on that is in the level curve that goes in the direction. So in this case, what you would think about is if I take the tangent vector here, this tangent vector would be in the same exact direction as I would continue going on this level curve. That would be the direction I would have to travel to continue going on. The gradient then is perpendicular to it. And this is true everywhere. Gradient of f. So similarly here, the tangent vector would be something like this. The gradient would be here. The tangent vector would be here. The gradient would be there. The gradient is always normal to level curves or to level surfaces, as we just saw previously. And this is from this exact formula. It all stems from this idea of dot products, which is kind of crazy that, such stuff back in 12.3 comes up so much here. So if you ever want to find or draw the gradient, what you do is you draw it perpendicular to just the contours you have there at a specific point. And that gives you a lot of really interesting information from that. So what did we kind of tackle here? We tackled the idea of directional derivatives. This idea of directional derivatives comes from the fact that how fast is my function height changing if I go in a specific direction. We saw that it's weighted based off of this gradient, right? Fx and Fy. And this works for Fx, Fy, and Fc. We also need to make sure always that this u is a unit vector. If it's not a unit vector, we must make it so. Always check. Always check. It's never a bad thing to check. We also saw that the gradient gives us some really interesting information. It tells us the direction of maximal increase, where am I going to be increasing the fastest, as well, where am I going to, in a three-dimensional sense, it also tells us, the normal vector to my surface too. It gives us an idea of approximation of a tangent plane. And lastly, and one of the more important things, I think, is this concept of gradients and level curves. And for those of you who are in some computer science backgrounds, there's a method to solve a matrix system in computations called the conjugate gradient method. And the conjugate gradient method deals with this gradient to basically find a maximum. Because what you can do is if I start to create my level curves here, let's say I create my level curves here. This is just something that's a little bit interesting though. What you can do is, as you note here, you can probably see that there's probably going to be some maximum here or a minimum. Because as I get level curves, as they go higher, right, we have to assume that they go in the same direction. If I'm starting here and I want to get to this peak, it might not be more beneficial to go just in this direction, right? You would think it is, but as you can see, it's probably not, because what I want to do is I want to keep going in the direction of the level curves. I want to keep going orthogonal to my level curves always. And if I keep doing that, if I keep going orthogonal to my level curves, I'm going to approach this from the least amount of steps possible. And what I can do is if I keep finding orthogonalities, and I keep just doing orthogonal things, it'll get to my answer more and more as I get to higher matrix values too. I'll get faster and faster. So gradients are really important. And also just in general, right? If I want to get to the top of a mountain, how do I get there? Well, just go as fast as possible and find the maximal route. And if you actually draw that out by taking topographical maps, you can find that you would always just be going the fastest when you're going orthogonal to your level curves. Yeah, that's kind of the concepts. Let me know if you have any questions. Post on Piazza or anything like that. And I hope you guys have a great day and enjoy your Saturday. And yeah, have a great one.